Essential Linear Algebra for Quantum Computing. This is your Professor Atif Reed Muhammad. This is lecture 3 in the series of quantum computing lectures as we are looking at Marshall University in West Virginia. Revisiting mathematics is significantly important because we will be utilizing several mathematical notations in terms of algorithms and solving the problems associated with quantum computing. Mathematics is necessary because we are moving or transitioning from classical computing, which is 0 and 1, to quantum computing, which is 0, 1 and beyond. So let's dive in. This module reviews the essential linear algebra concepts required for understanding quantum mechanics and quantum computing. Topics include vector spaces, inner products, linear operators, matrices, eigenvalues, and eigenvectors. We will explore how these mathematical tools are used to represent quantum states and quantum operations. We have looked previously at the bits and qubits and how the state change can happen. We will be looking at the quantum automata in quite depth in the upcoming lectures as well. Emphasis will be placed on complex vector spaces and Hermitian operators, which are fundamental to quantum mechanics. You will learn how to perform matrix operations and solve eigenvalue problems, skills that are crucial for analyzing quantum algorithms and quantum circuits. So let's just dive in. We will also looking at essential linear algebra for quantum mechanics and computing in more depth, as well as foundational tools for quantum algorithms and circuits, and last not the least, exploring vector spaces, matrices, and eigenvalues. This is to reiterate that this lecture is of significant value for us to learn from. Vector spaces. A vector space is a collection of objects, vectors, that can be added together and multiplied by scalars, which are numbers. It follows specific rules like closure, associativity, and distributivity. Imagine arrows in 3D space. You can add two arrows together or stretch them by a factor and they still remain in the same space. Vector spaces are the stage where quantum states perform. Understanding them helps us describe how quantum systems evolve. Let's look into this with a real example that is hypothetical till we apply a Python code in Google Colab. In classical computing, a vector space is simply a collection of numbers arranged in an ordered list, like coordinates on a map. Imagine you are running a movie streaming service and want to represent each user's preference or preferences. You might create a vector where each position holds a rating from 0 to 5 for different genres, 4 to 5, 1, 3. Let's say this is your first set of ratings. Could mean a user loves it's technically, let me repeat myself. So 0 to 5 is a standard bifurcation. Out of 0 to 5, I have looked at 4, 2, 5, 1, 3. Could mean a user loves the action as 4, dislikes romance as 2, is obsessed with sci-fi as 5, barely tolerates horror as 1, and enjoys a comedy as 3. These vectors live in a mathematical space where you can add them, scale them, and measure distance between them. When your recommendation algorithm compares your vector to other users' vectors, it is performing operations in this vector space to find people with similar tastes. Classical computers manipulate these vectors using standard arithmetic operations. You can add two vectors together, component by component, multiply them by numbers to scale them up or down, or calculate the angle between them to measure similarity. In our streaming example, if two users have vectors that point in nearly the same direction, small angle between them, they probably have similar preferences. So the system recommends movies that one user loved to the other. This works great for many applications, for predicting what you will buy next to recognizing faces in photos. The vectors are concrete, defined, and definite lists of numbers defined by these vectors stored in your computer's memory, and all operations follow predictable deterministic rules. Quantum computing transforms this picture completely by allowing vectors to exist in superposition, meaning that they can represent multiple states simultaneously until measured. In quantum system, instead of using a user's preference vector being fixed at 42513 as we discussed earlier, it could exist as a combination of many possible preference patterns at once. This happens because quantum bits or qubits can be in states like both 0 and 1 rather than just one or the other. When you run a quantum algorithm on these superposed vectors, you are essentially processing all those possibilities in parallel. The catch is that when you finally measure the result to get an answer, the superposition collapses to one definite outcome. This makes quantum computers potentially powerful for specific problems like searching through massive databases or optimizing complex systems, because they can explore many solution paths simultaneously before converging on the best answer. Complexity. Complex vector spaces extend real vector spaces by permitting complex numbers as scalars. They are essential for describing quantum states, which often involve complex probabilities, as I just mentioned in the moving streaming thing. Think of a complex vector space like a 3D graph, but with an extra imaginary dimension, permitting more flexibility in representing quantum information. Quantum mechanics relies on complex numbers to describe probabilities of states, making complex vector spaces fundamental to the field. Inner product spaces. Let's dive into this in more depth. Before I dive into the inner product spaces, let's look into the complexity with a real possible example. The complexity of quantum vector spaces grows exponentially in a way that makes classical systems look simple by comparison. In our movie streaming example, if you represent just 10 user preferences classically, you have 10 separate numbers to track. But with 10 qubits in a quantum system, the vector spaces has 2 raised to the power 10, that is 1024 dimensions, meaning that you need 1024 numbers to fully describe the quantum state. This explosion happens because qubits can become entangled, where the state of one qubit depends on the states of others in ways that cannot be separated. Imagine if a user's love for action movies was mysteriously linked to another user's comedy preferences in such a way that knowing one tells you something about the other, even though they have never met. With just 50 qubits, you would need more numbers to describe the quantum state than there are atoms in the observable universe. This massive dimensional space is both quantum computing's greatest strength and its biggest challenge. It permits quantum algorithms to explore an enormous number of possibilities at once, potentially finding optimal movie recommendations across millions of interrelated preferences patterns simultaneously. It also means that simulating that quantum computer does on a classical computer becomes impossible beyond a few dozen qubits, and any noise or errors in the system can corrupt this delicate high-dimensional state. Now let's look into the inner product. An inner product is a mathematical operation that takes two vectors and produces a single number that tells you how similar or aligned they are. In our movie streaming service, when we calculate the inner product of two user preference vectors, we are essentially multiplying corresponding elements and adding them all up. So if someone has an exact opposite taste that with vector 15042, the inner product would be much smaller, indicating these users should not receive the same recommendations. This concept is fundamental to machine learning algorithms that power modern recommendation systems, where computing millions of inner products help identify clusters of similar users or find the best matches between a user's history and available content. In quantum computing, inner products takes on special significance because they help us understand the probability of measuring different outcomes and the relationships between quantum states. When we have two quantum states represented as vectors in that exponentially large space we discussed, their inner products tell you the probability amplitude of transitioning from one state to another. Back to our streaming example in the quantum realm, imagine each possible combination of user preferences across our entire platform exists in superposition. The inner product between our current quantum state representing all users simultaneously and a target state representing an ideal recommendation configuration gives us information about how likely our quantum algorithm is to collapse into the desired outcome. What makes this powerful is that quantum computers can compute these inner products for exponentially many states at once. So this is something that we are going to do hands-on in our upcoming classes. So, and as mentioned on the slide, an inner product space is the math that lets us measure overlap between quantum states. It turns superposition and probabilities into precise rules, unlike classical bits, which are just 0 or 1. This overlap math is the core reason quantum computers can be more powerful. The norms and orthogonality. Norms ensure a quantum state's total probability equals 100%, keeping the math consistent. Orthogonality means two states are perfectly perpendicular and can be told apart with certainty, like a classical 0 and beyond and 1 and beyond. Together, they form the reliable geometric backbone that makes quantum measurement and computation possible. Let's look into our streaming example to understand norms and orthogonality in quantum computing in a little bit more detail. In quantum computing, the norm of a vector represents its length or magnitude, and there is a critical rule that quantum state vectors must always have a norm of exactly 1, which is called normalization. Think of our streaming service where each user's preference vector has a certain strength measured by its norm. If a user A's vector is 4, 2, 5, 1, 3, the norm is the square root of 4 4s are 16, 2 2s are 4, 5 5s are 25, 1 1s are 1, and 3 3s are 9. When we add all of that, which equals to 7.4 in quantum systems. So technically that equals to a certain number, and that is calculated in quantum systems. We must normalize this so probabilities work correctly. When you measure a quantum state, the squared norm tells you the total probability of all possible outcomes. So it was 7.4. And since probabilities must add up to 1, the norm must equal to 1. Orthogonality is equally important because it describes when two vectors are completely perpendicular to each other, meaning their inner product equals 0 if two users have orthogonal preferences. Vectors, they have absolutely nothing in common in their tastes. In quantum computing, orthogonal states are perfectly distinguishable and represent mutually exclusive outcomes. For example, a qubit being definitely in state 0 is orthogonal to its being definitely in state 1. Just like a user who only watches documentaries, so 0, 0, 5, 0, 0, so only watches documentaries, is orthogonal, or to someone who only watches the animated films. So that can be 0, 0, 0, 0, so 4 zeros and 5. Quantum algorithms exploit orthogonality to separate different answer possibilities cleanly, ensuring that when you measure the system, you get one clear result rather than muddled mix, much like how your streaming service wants to give you one specific category of recommendations rather than confused noise. The example here is in a quantum pizza shop, every pizza must be whole 100% pizza. This is another example. That's the norm, keeping probabilities sensible. Cheese only and pepperoni only are perfectly distinct. That's orthogonality, like 0 and beyond and 1 and beyond. So the states in a qubit. But a quantum pizza can be in a blended both at one state, giving you more information and possibilities than a classical pizza menu ever could. Linear operators. This is another area that I would suggest you to look into conducting research at Google Scholar or IEEE Explorer to find more in depth. Linear algebra provides a mathematical framework for quantum mechanics and computing. It involves vector spaces, matrices, and operations that describe quantum states and transformations. Think of linear algebra as the grammar of quantum mechanics. Just like grammar, rules help us construct meaningful sentences in a language which we use to speak, whether it's English, French, Spanish, or something else. Without linear algebra, we couldn't model quantum systems or design quantum algorithms, which are key to advancement in computing, cryptography, and physics. And so linear operators are significant in that aspect. Matrices. Matrices are rectangular arrays of numbers that represent linear operators. Each entry in the matrix defines how the operator transforms the basis vectors of a space. In animation, matrices are used to rotate, scale, or move characters smoothly across the screen. You can think of a gaming console. Matrices allow us to perform calculations efficiently, making it possible to simulate and control quantum systems. So matrices are tools for organizing numbers into rows and columns. Again, this is a revisiting of our mathematics. They represent linear transformations and are used to solve systems of equations. Spreadsheets use matrices to organize data, permitting you to perform calculations across rows and columns efficiently. We all have used spreadsheets in our everyday, past, present, and more likely future. We'll be using these as well. Matrices are fundamental to quantum mechanics, where they represent operators and states, enabling us to model complex systems. Unitary operators. Unitary operators are special linear operators that preserve the length of vectors. They are invertible, and their inverse is equal to their conjugate transpose. I'm not going to go into details. I would strongly suggest you to visit your previous mathematics lectures or read some books which have unitary operators to understand and establish the understanding for classical computing at the moment, because we'll be utilizing these things in our quantum computing in our coming discussions. Spinning a globe does not change the size of or the shape of the continents. Unitary operators work similarly, preserving the properties of quantum states. Unitary operators are the building blocks of quantum gates, ensuring that quantum information is processed without loss or error. This is also helpful in our future understanding of quantum error reduction. That's a whole area of expertise that one of you or all of you can actually expand upon and be the subject matter experts. Matrix operations. Matrix operations include addition, subtraction, multiplication, and inversion. This is just for the revision's sake. These operations allow us to combine and manipulate matrices to solve problems. When you apply multiple filters to a photo, your phone uses matrix operations to combine those effects seamlessly. Matrix operations are essential for performing calculations in quantum mechanics, such as simulating particle interactions or quantum gates. Hermitian matrices. Hermitian matrices are equal to their conjugate transpose, and their eigenvalues are real numbers. They represent observable quantities in quantum mechanics. Think of a mirror that reflects an object without distorting it. Hermitian matrices act similarly, preserving certain properties of quantum systems. Hermitian matrices are tied to measurable properties in quantum mechanics, like energy or position, making them critical for experiments and theories. Let's dive into this to understand a little bit in more depth. So since we are discussing the Hermitian matrices, these are special mathematical structures in quantum computing that represent measurable properties or observables, and these are crucial because their eigenvalues, special numbers associated with the matrix, are always real numbers, as mentioned earlier, which is exactly what we need for actual measurement results. In our streaming service example, which is continuing in this lecture, imagine you want to build a quantum algorithm that measures overall user satisfaction across your entire platform. You would encode this as Hermitian matrix that acts on your quantum state vector representing all user preferences in superposition. When you apply this Hermitian matrix and perform a measurement, you don't get complex numbers with imaginary parts. You get real numbers like 7.5 or 3.2. That represents actually satisfaction scores you can interpret. The reason Hermitian matrix or matrices have this property is that they equal their own conjugate transpose, which is fancy way of saying they have perfect symmetry when you flip them along their diagonal and take the complex conjugate. The same example, looking in the mirror, not while the image has not been distorted of yours. Think of it like ensuring your satisfaction measurement treats all users fairly and consistently, regardless of which direction you analyze the data. In practice, quantum gates and operations are often represented as Hermitian matrices because they preserve the normalization of quantum states and give us real value results we can actually use, like determining whether to recommend a blockbuster or an indie film based on the eigenvalues that emerges from the measurement that we have looked into. Eigenvalues and eigenvector. Eigenvalues are scalars that indicate how much an eigenvector is stretched when a linear operator is applied. Eigenvectors are the directions that remain unchanged. Imagine stretching a rubber sheet. Eigenvalues tell you how much it stretches, and eigenvectors show the directions of the stretch. Eigenvalues and eigenvectors help us understand stability and transformation in quantum systems, which is vital for designing quantum algorithms. Solving eigenvalue problems. Solving eigenvalue problems involves finding the eigenvalues and eigenvectors of a matrix. This process is key to understanding the behavior of linear operators. Once again, this is the revisiting of standard mathematics and its applications and implications within the classical computing and extensibility of this mathematics into quantum computing. Engineers solve eigenvalue problems to determine the natural frequencies of bridges, ensuring they don't resonate dangerously in the wind. Because when we are driving on a bridge and if it is resonating due to the wind or something, what will happen? What can possibly be happening when we are driving? In quantum mechanics, solving eigenvalue problems reveals the possible states and energies of a system, which is crucial for predictions and experiments. Spectral decomposition. The spectral decomposition breaks down a matrix into its eigenvalues and eigenvectors. It simplifies complex matrices into more manageable parts. Now, I have specifically mentioned real life example and why should we care in the spectral decomposition, because we are entering into literally on a very slow pace in complex terminologies. Think of a spectral decomposition like disassembling a clock into its gears and springs to understand how it works. Why should we care? Spectral decomposition helps us analyze quantum systems by breaking them into simpler components, making it easier to study their behavior. So now we come back to revisit the Hermitian operators. The Hermitian operators are linear operators that are equal to their conjugate transpose as mentioned earlier. They have real eigenvalues and orthogonal eigenvectors. A perfectly balanced seesaw is like a Hermitian operator. It maintains equilibrium without favoring one side. Hermitian operators represent physical observable in quantum mechanics, such as energy or momentum, which are critical for experiments. I would strongly suggest you to conduct a research on experiment design using classical computer and see what happens. Alright, let's move on. Eigenvalues of Hermitian operators. The eigenvalues of Hermitian operators correspond to possible measurement outcomes in quantum mechanics. They are always real numbers. When you measure the temperature of water, you get a real number. Similarly, Hermitian eigenvalues represent measurable quantities in quantum systems. So why should we care? These eigenvalues provide the possible results of quantum measurements, which are essential for interpreting experiments and developing theories. So if you are going to cross a cross-country drive and you are heading on a highway and that hits a T, there's no highway continuing. You're not on a horse and you don't know what lies beyond that T. You're driving. You will either go right or you will go either left. That is 0 or 1. However, when you develop a theory and somehow at this moment you expand your flying car's wings, you can take off and go straight and see what is beneath you, because now you're flying in the air. Your dimensionality has been changed. The quantum states are represented as vectors in a complex vector space. They describe the conditions of a quantum system, including probabilities of different outcomes, as we are discussing about the movie streaming business, and we have looked at the probabilities earlier. Imagine a spinning coin in midair, as we discussed in our previous lectures. Its state is a combination of heads and tails until it lands. Understanding quantum states allows us to predict and manipulate the behavior of particles, which is foundational for quantum computing. We will look at quantum automata in quite depth in our coming lectures. See you in the next class or next lecture. Stay tuned, learn more, and make sure that you are conducting a research on classical computing before even transitioning to the quantum computing.